So first, it's my great pleasure to speak right after Professor Chen. And today I would like to spend a very short period, like 10 minutes, to share with you guys about our recent works applying machine learning energy models to study the nanomaterial mechanics. So I know that some of you guys missed the movies at the first place, so I would like to replay this. So just to echo Professor Chen's the last topic. So this is dislocation. So this is the molecular dynamics simulation of a dislocation gliding through a chemically complex alloy. And as you can see, this the distorted region is actually amorphous and hexagonal closed-packed region. So it's chaotic. So I'm going to talk about this briefly in the later part of my talk, if I didn't use all of my time. Okay, so the first difficulty we face is that how can we, as you know, that in atomistic simulation, we need to have an interatomic energy model to describe the interaction between atoms in the system. So this is the energy partitioning scheme proposed by Bader and Parinello. So this is scheme. So start from Cartesian coordinate of atoms, so we can encode them into a rotationally and translationally invariant vectors G, and they actually look like this. So basically, we include both the pair interaction and the three-body interaction, and then we can let all these feature vector embeddings passing through all these atomic neural networks, and then this neural network looks like this, and then pass through, and we have the total energy of the whole system. So we use this scheme to train a neural network model of this FAMAPPIBR, and as you can see, this is a very complicated mixed-ion perovskite. So these are done by my former students and my former postdoc, and this is very complicated material you see. So MA actually looks like this, and the FA actually looks like this. So you can see that by using neural network, we can train an energy model. So the horizontal axis shows the ground truth from VASPA calculation, and the vertical axis shows the prediction from neural network. And you can see that the parity is pretty good. And we can also have a very good parity between atomic force. And then we can, because this is much faster than the DFT calculation, and it's almost as accurate. So we can use that to do extensive sampling over the compositional space. So this is the concentration of chromium, and this is the concentration of methyl ammonium. And then we can isolate all the low energy structures and use them to compute the band gap and compare with the experiments. And then furthermore, because the neural network model is very efficient and it's very fast, and this allows us to map a lot of physical and mechanical properties of this complex perovskite, and we can use that to build a Pearson correlation matrix, which basically allows us to figure out, to reveal the process structure and the property relationship of this complex perovskite material. So we can find the correlation between the concentration of constituents and between this structural properties like shear strength and the volumetric strength, and then finally about the property. So we can use to find out the composition regime that can potentially lead to phase segregation and the relatively poor device performance. And then the next one is that so recently we have joined work with Professor Solovitz and Professor Yang Yong at Hong Kong, and they synthesized this chemically complex alloy with a very high elastic limit. And the most interesting thing about this alloy is that when it's upon plastic deformation, it can show both the crystalline phase shown, where? It can have a crystalline phase and also, as you can see from here, an amorphous phase. So when it is yield, it can have both crystalline and amorphous phase. So we want to study the large scale plastic response of this material. So we use another machine learning based energy model called the spectral neighbor analysis potential. And it is similar to the artificial neural network. So we start once again from Cartesian coordinate, and then we convert them into another set of feature vector or embeddings. Now this is called, then we're just running away. So we convert them into bispectrum components, and then once again pass through a linear summation with this very simple, or you can say it's equivalent to a one-layer neural network, and then we can obtain once again the total energy. And so this is done by my current postdoc, and this is basically the training flow. So we once again start from a large set of quantum chemistry training data, and then feed all these parameters. And once again, these are the training results. So this is the energy from multiple calculation, and the energy predicted from this snap potential model. So they are in very good agreement, and this is atomic force. And with this, we can perform very large scale. So this result are from DFT calculation, and these are basically the size limits that allow us to use DFT. But using the chain, the machine learning potential, we can do this. And this is the simulation of a compression of a nanopillar of this alloy. And you can find dislocation, nucleation, and the formation of amorphous shear band. So this is identical with the experimental observations. And once again, so this is the viewing from the top. So you can see dislocation propagate through this nanopillar. And we can also stimulate dislocation dynamics. So you can see dislocation glide through and leave a bunch of defects behind. And we can also identify the core structure of a screw dislocation and edge dislocation. So it basically looks like this. And the Burgers vector, so I didn't mention that in my slide, but the Burgers vector predicted from neural network, from this snap potential is the same as that observed from experiments. And then we didn't put the dislocation, the structure with dislocation into the training set. Okay, so this is the summary of my talk. So this is the accuracy. This axis shows the accuracy, and this axis shows the system size, and this shows the time allowed for simulation. So you see, so this is very small, and this is well, I think right now this one should shift a bit leftward. But anyway, so for DFT calculation, you can have very high accuracy, but a very small size, and a very short simulation time. But for classical MD simulation, the accuracy is kind of doubted, and but however, you can simulate a very large system size, and if you have a very specialized machine like Anton, you can simulate a very long time. But the accuracy is a real problem. So by using machine learning energy models, we can have a very high accuracy compatible with the DFT calculations, and smaller system size, and a little bit shorter time scale comparing with classical MD simulation. So that's all I want to share today, but I still have one more last slide because my colleagues strongly asked me to show the last slide. And I'm going to speak that in Chinese. Oh, I'm sorry. Wow, that's funny. I'm sorry. I forgot. Well, because this is the file I uploaded in the morning, okay. But I changed the file a bit in the during the lunchtime. But anyway, I did my job. But Can I use like 1 minute for advertisement? OK， 我最后一张 slide 其实是那个中研院应科中心有暑期大专生实习计划，所以欢迎各位大学部同学有兴趣的可以去申请。然后我要强调一件事，就是说。我们其实非常欢迎工学院的学生，因为大家会觉得中研院好像就觉得应该是物理、化学 whatever 嘛。可是其实呢，我们也很非常欢迎工学院的学生去参加。然后应该是明天或后天晚上了，我想想看，哦，对，明天晚上在台大有一个说明会。然后很不幸，这个他都已阅读。好，这就我今天要分享的。Thank you very much。我这个首先呢是我要强调一件事情是，我这个只是经验公式。This is just empirical, because I think at this, what machine learning potential is still more complicated in terms of format. So I don't think it can be compared with that of classical MD in terms of system size as well as simulation time. Because for classical MD simulation, once they just throw out the Lennard-Jones potential, then nobody can compete. Yeah.
好，那我们的。
我觉得可以再加一个轴，是有关于它的应用的拓展方面，就是今天是在这个 system 之下，那如何应用到别的 system 的时候，它可不可以承接这个部分？
哦，你是说那个 transferability 吗？对，这个是一个很好的那个问题。不过我这张图是在点找，一时之间找不到别的地方可以塞。
好，那我们就对，谢谢包老师。
OK，谢谢。